start our discussion for today. Today's topic is similitude and model analysis. So as I said that dimensional and model analysis, these two concepts basically helps us to design the experiments because most of the physical phenomena cannot be fully understood from the theoretical point of view. But when we do the real experiments, we get the real data and we can really simulate the actual flow phenomena if certain kind of condition is existing in a certain domain. So for that purpose, experimental things need to be decided, and when we are carrying out the experiments, we cannot put an entire full scale model, full scale actual device. We have to go for a small scale replica of the same prototype, and that is basically called model. So when we are putting the model in our experimentation, the equation, right, that will be denominating in the flow need also be to be derived again. So we will find out the number of variables which are going to influence on the expected results, and we will derive to get a relationship among those variables, and finally we will predict the flow behavior, how flow is happening on the model, and the same thing can be extrapolated to get the extended results on the actual prototype. So the first topic in this is basically similitude. Similitude is the concept basically used in testing of the engineering model. So similitude is talking about something called similarity. So similitude is basically similarity between model and prototype. So when we talk about prototype is called actual device, right? If you are talking about automobile car, full-fledged dimension car that usually we see, which is running on the road, that is called actual device, or we can say prototype. But model will be the small replica of the actual prototype. So small replica, when you are saying that, the length and width will be bearing a certain relationship with the actual length and actual width. So it will be reduced size, model, but the flow behavior, if we are able to get on model, can be extended to the flow behavior on actual prototype. And for that purpose, the similitude, helps us a lot. So similitude is the concept used in the testing of engineering model, right? So example, like if we consider the ships in towing machines, right? So when we are carrying out the flow analysis or going to find out the behavior of the ship, we cannot put an exact ship size, right, big size into the wind tunnel or water. We have to reduce it, right, to get a model. Like aircraft in wind tunnel, we cannot put full-fledged aircraft, so we'll be using the model of it, right? Small replica of it inside the internal hydraulic turbines. Similarly, when we are going to design the blades used in the hydraulic turbines, we have to do the flow analysis, right, within the casing of the hydraulic turbines. So that is also flow analysis, right? So when you are doing it, we can take small model and we make the flow to happen and see how flow is interacting in the blade passages, and how much amount of resistance is going to be created that can be minimized by changing the geometry of the blades. Similarly, centrifugal pumps, spill basin dams, river channels, etc., can be studied right at a small scale model basis, right, using the concept of similitude. And apart from that, we can also study the action of waves and tides on beaches, soil erosion, and transportation of sediments. That can also be studied with the same concept of similitude. So when we talk about model analysis, right, as I said that for experimental purpose, we always consider the small scale replica of the actual structure. So if you look at this, so model is defined as the small scale replica of actual structure or machine. It is not necessary that model should be smaller than the prototype always. Sometimes it may be bigger, right? Sometimes it may be bigger. So prototype is called actual structure or machine. So model analysis is the study of models of actual machine is called model analysis. What are the advantage of it? Advantages include the performance of machine can be easily predicted in advance. So if you want to get the actual performance of machine well in advance, you can get the information about that. So with the help of dimensional analysis, the relationship between the variables influencing the flow problems in terms of dimensional parameters is obtained, This relationship helps us in conducting the test or the model. The merits of alternative designs can be predicted with the help of model testing, and most economical and safe design may be finally eroded. That means model is a small replica. You can repeat it again. You can get n number of models and you can carry out the experiment. Let's suppose on some design, if you are finding that it is creating more resistance, right, air resistance. If we talk about in the case of fluid mechanics, which is basically dealing with the liquid. So if we are putting the same model inside the water flow, and if we come to know that it is creating a lot of resistance, we can modify the design again, but at the small scale. So like that, slowly, if you do design modification to the model, you will come to an optimum design at which you will be getting the better performances. So that is the main purpose here. The third point, which is actually accounting for that, the merits of alternative designs can be predicted with the help of model testing. So most economical and safe design may finally be adopted. So you can do n number of repetitions, right, with the smaller size model. If you put the actual size, cost-wise, it not be effective, and that much size, bigger size, experimental setup you have to fabricate, that is also very difficult. That's why always will go for the smaller scale model testings. This is one concept. So as we have already said that model and prototype, you might be knowing now difference. So it's a small scale replica of actual structure. So let's suppose the spillway through which water is going, this is the actual model, right, which is having length of LP1 right over here and LP2 somewhere here, and force is acting like this. So all these parameters, right, all these variables can be scaled down to the smaller size, and which is basically called as model. So here this length will be bearing a certain relationship with the length of the actual model that we will define, right? So length ratio, velocity ratio, force ratio, all those things will be defined. So force on model will be having some multiplication of the force on prototype, that is called actual model, actual device. So that concept, basically interrelationship that we are going to develop, is called similitudes. Now similitudes can be further divided into three categories as we studied, right? One is called geometrical similarity, right? When geometry, we are just comparing length and width of the prototype and length and width of model. We are just comparing. If they are bearing certain relationship, we will say that the geometrical similarity, similitude or similarity. And if you talk about kinematic similarity, kinematic actually talks about the velocity and acceleration. So velocity acceleration on the surface of model and surface of the prototype, if they are varying certain relationship, we say that as a kinematic similarity. When we talk about dynamic similarity, where basically your force will come into the picture, different kind of forces, inertial forces, viscous forces, rotational forces. If the ratio of those forces on model and prototype we have certain relationship, we'll say that as a dynamic similarities, so or dynamic similitude. So they can be further divided into three categories, right? So that we will discuss on. Then classification of model. Further, you can classify model into two categories. One is called undistorted model, and is called distorted model. So when we talk about undistorted model basically talks about when models which are geometrical similar to their prototype. Or another way you can say, if you are measuring the dimensions on horizontal direction or vertical direction, they will have a similar value, right? Linear dimensions you'll be getting. But in some cases, right, when we are designing the model, it will not be possible to put the same dimension in across two different directions. One direction, distance will be lesser than the other direction, and those kind of models will be called distorted models. So distorted models are those models which are geometrically not similar to its prototype. In other words, you can say the scale ratio of the linear dimensions of the model and its prototype are not same. So, for example, if we are simulating the river flow, so in river flow exactly we cannot put length equal to width, right? Means across the length direction, scale ratio may be different along with direction. Your scale ratio will be different. So when we are simulating the river flow, right, we'll have to go for distorted kind of model concept. So if the horizontal and vertical scale ratio for model and prototype are same, then it's called undistorted, right? And In the case of rubber, we cannot do that, so we can go for distorted model. So thus, in this case, distorted model is useful. So these are the two classification of models. If you come to the types of similarities, as I already told you, similitude is defined as similarity between model and prototype in every respect, which means a model and prototype have similar properties, or model and prototype are completely similar. That possibility is also there. So these are three types: geometrical, kinematic, and dynamic similarity. So one by one we'll see. So first is called geometrical similarity. It is the similarity of shape, right? So it is said to be exist between model and prototype if ratio of all corresponding linear dimensions in model and prototype are equal. So length by length and width by width and height by height. If you take the ratio, if they are exactly equal, you can say geometrical similarity. So for example, is this length of prototype divided by length of model is equal to width of prototype by width of model, and depth of prototype by depth of model is equal to, this is known as LR. So when we are talking, this LR is nothing but skill ratio. So here all these are length, width, and diameter. Especially diameter talking about, depth is not, this is not depth, this is diameter of prototype. And similarly for model, if this ratio is exactly equal, we get a relationship which is known as scale ratio, right? LR is called scale ratio, geometrical scale ratio. We have defined one parameter over here. Next one, kinematic similarity. So it is a similarity of motion. So it is said to exist between model and prototype with the ratios of velocity and acceleration, right? Velocity and acceleration at corresponding points in the model and prototype are equal. So we can represent like this: velocity at first point on the prototype divided by the velocity on the same similar point on the model is equal to velocity at second point on the prototype surface divided by this velocity on second point on the model. This ratio is basically known as velocity ratio, right? V suffix R. Similarly, for acceleration, you can write the relationship in a same ideology. So AP1 by AM1 is equal to AP2 by AM2 is equal to uh, acceleration ratio or acceleration scale ratio. So AR we can define. So all these terms, you can say like these are our velocity and acceleration. So you can explain those: BP1, BP2, AP1, AP2 are the velocity acceleration at point 1 and 2 on prototype. Similar parameters are there on the surface of model. And VR and AR is known as velocity ratio and acceleration ratio. And these things you have to keep in mind, these all skill ratio, right? In geometrical case, we define the skill ratio simply, or geometrical skill ratio, you can say. Here we have defined the velocity ratio and acceleration ratio. Last one is called dynamic similarity. When we are talking about dynamic similarity, we'll be talking about the force causing that motion, right? Usually. But in kinematics, we were not considering the force, so we were considering only velocity and acceleration. So dynamic similarity is the ratio of basically forces. So it is said to exist between model and prototype. Ratios of forces at corresponding points in model and prototypes are equal. So we can say inertial force, Fi is called inertial force on prototype divided by inertial force on model is equal to the viscous force on prototype, and viscous force on model is equal to gravity force on prototype divided by the gravity force on model, and this ratio is known as the force ratio, that is denoted by Fr, and all these parameters are having their own meaning, right? So it is written over here, Fr is called force ratio. Now problem is that in most of the cases, inertial forces dominate, right, always on other kind of forces, because viscous forces will be dominating only in very thin region near the solid surface where boundary layer, formation takes place. And gravity force, in most of the cases, gravity force is usually considered to be constant because it is coming due to the weight of the fluid medium, which is basically not going to change along the length of the flow. So in most of the cases, inertial forces actually dominate over others. So the force ratio is basically, in most of the cases, we say inertial forces ratio on prototype and model. But depending on the situation, right, the practical situation, you can select the type of the force which is basically predominating, right, in certain phenomena. In some cases, when you are studying the flow within the boundary layer, right, effect, in that case, inertial forces will not be there. Gravity forces cannot be considered. Only this will be the ratio of viscous forces, right, as prototype and model. If you are studying any flow phenomena, right, exactly on the surface of the liquid, right, in the river, and the surface of the river, right, water usually, which kind of force usually acts, that is called surface tension force. And surface tension force comes due to the surface tension effect. So that will be one of the predominating factor in the case of surface forces when you are going to find out. So you'd have to take the ratio of surface tension force on prototype and surface tension force on the model. So like that, you have to actually determine which force is dominating under what condition. Based on that, you will select the force ratio. So types of forces basically type forces can be subdivided into various types depending on the nature, right? Inertial force, gravity force, surface tension force, viscous force, rotational force, pressure force. So one by one we'll see. So first is called inertial force, that is represented by the F suffix I. It is basically equal to the product of mass into acceleration. That's what usually we say. Mechanical force also, that is self is called inertial force. So certain mass, if it is able to move by certain distance, right, by a certain, kind of additional external force, that is called inertial force. So first is the inertial force. Second is called viscous force. Viscous force will come within that small thin region. So it is basically equal to the shear stress developed due to viscosity into the surface area of the flow. Next one is called gravity force. It is equal to the product of mass into acceleration due to gravity. So due to the weight of the fluid, right, gravitational force come to the picture. Next one is called pressure force. It is equal to the product of pressure intensity and cross-sectional area on which that pressure is acting on. So this is the product of that denoted by the F suffix P. Surface tension force, it is equal to the product of surface tension and length of the surface of the flowing fluid. The surface tension force. Last one is called elastic force. It is equal to the product of elastic stress into the area of the flowing fluid. So this, when we are talking about elasticity for the fluid, that is called liquid, usually we define in terms of bulk modulus. The bulk modulus itself will be representation of your what do we say, the elasticity, right, in the case of liquid. So it is basically equal to elastic force is equal to the elastic stress and into the area of flowing fluid. So these are the various types of forces you will be encountered when you are doing the experiment on any kind of model in the fluid flow domain. Don't get confused, right? You have seen now clear difference between various kind of forces. So now dimensionless numbers always be it is good to represent variables in terms of non-dimensional term, because when we are using the dimension which is having some dimensions, and the dimension will be actually varying with the variables, right? Let's suppose some dimension is there which is having pressure and volume and temperature within it. So if you are changing one parameter out of this, right, your dimension magnitude will be varying. So in order to avoid certain kind of local changes in the dimension, we always prefer to have dimensionless numbers. So dimensionless numbers doesn't depend on the variables changes, right? If any variable changing, there will be no effect on actually dimensionless number. Directly it will not have. So at a single, if you want to draw the behavior, right, if we are not considering the non-dimensional terms, right, of the variables, in that case, for every location you have to draw a single curve. So like if I'm saying that if I'm analyzing a flow of just 1 meter, if I'm dividing that into 10 different segments, then I will be getting the 10 different kind of curves of flow behavior. So it is very difficult to finally come at the conclusion that this is the net effect which has happened within the given length of the flow. So in order to avoid that, usually we consider the non-dimensional, magnitude of the variables, so that I will be getting a single curve which will be explaining the entire flow behavior which is happening within the given length of flow. So non-dimensional terms, when we are talking about, usually we get that by the ratio of equal magnitude. So if we divide force by force, we'll get one non-dimensional term that is called force, right? It's a representation of force, but it is in the term of ratio. So as the ratio of one force to another it will be called dimensional number, and this is called as non-dimensional parameters, right? Non-dimensional parameters, and always we refer this non-dimensional parameters. So these are the certain examples of non-dimensional numbers: Reynolds number, Froude's number, Euler's number, Weber's number, and Mach number. Now Mach number will come to the picture, which I was talking about earlier. So Reynolds number already been introduced to you, right, in the viscous flow, where we defined, right, Reynolds number is the ratio basically inertial y viscous. And we got certain relationship called rho v d upon mu or rho v l by mu, which is known as Reynolds number. And based on the Reynolds number, we can define the flow behavior like laminar, turbulent, transitions. Those all can be determined with the help of Reynolds number. Second is the Froude's number. This will come in the effect when flow is taking place in the open channels, right? When flow is taking place in open channels, it will be accounting for two forces, right? Gravity force and pressure force. Because it is atmospheric condition, gravity force will be present, and due to the pressure, your flow will be moving. So pressure force and gravity force ratio will give you the Froude number. Similarly, Euler's number, we talk about Euler's number, you'll have elasticity into the consideration. Weber number, then Mach number. When you talk about Mach number, we'll be talking about the velocity. So velocity of local velocity of particular object to the speed of sound, right? What is the velocity of speed of sound at a given location? If you divide those, you'll get the Mach number. So one by one, we'll see all these numbers, and these are very very important. So based on these numbers, model laws will be defined, right? So Reynolds number model law, Froude model law, Euler model law, Weber model law, and Mach model law. So depending on the application, you can select any one of these. So first one is called Reynolds number, right? Is the ratio of inertial force to the viscous force, all right, of the flowing fluid. So if we divide these two forces, we can get so inertial force by viscous force. Inertial force is called mass into acceleration, right? So this is velocity divided by the time, and viscous force is shear stress into cross sectional means surface area. Is surface area, right? So this multiplication will give the viscous force. So this further can be modified, right, as density is equal to mass by volume. So mass will be written as density into volume, right? Density into volume in place of mass. If you write and they take this time inside downside of the volume. So volume by time is called basically flow rate, right? Volume flow rate in meter cube per second. Usually you study it, right? Meter cube per second. That is also known as discharge, right? Discharge. And discharge is nothing but area into velocity, right? Area into velocity. So what you have done, you replace the mass by density into volume and volume by time. This is basically becoming the discharge, right? Which usually represented by the Q that we know. And shear stress is represented by the tau, and this is the area. So this is simply we have written tau into A. But tau, that is shear stress, will get from the Newton's law of viscosity, right? In most of the cases, we consider the fluid to be a Newtonian fluid, and for Newtonian fluid, we always say it bears a linear relationship with the velocity gradient. So velocity gradient is velocity changes with respect to the length. So in place of tau, if you write mu du upon dy, where du is basically v divided by dy is called length into area, this entire term is tau into a. But if you look at the above, we are replacing this discharge by area into velocity. So we can write in this way rho area into velocity square divided by this term v and v will cancel out. If you do further modification, you will get rho vl upon mu, rho vl upon mu, which was the equation that we were using earlier. So rho vl upon mu, or further modification, you just take this density down of this mu upon rho. You can write this as velocity length divided by the kinematic viscosity. This is basically kinematic viscosity. Kinematic viscosity. That is mu upon rho. So this is known as Reynolds number. Next one is called Froude's number. It is the ratio of inertial force to gravity force. Inertial force to gravity force. If you take the ratio of these two, right, you will take the get the Froude number. So Fe is equal to under root Fi upon Fg. So Fi already you derive the expression for that as rho a v square directly you can write, and gravity force is mass into g, right? Mass into small g, and then you replace the mass by density into volume, right? That already you know. So if you put all this, you can get rho q v divided by rho into volume into c, and volume can be written as area into length, right? Area into length is called volume. If you replace over here within this bracket, so area and area cancel out, density cancel out, you will get v square divided by lg inside. So v can be taken out, so it will become v divided by under root gl, and this ratio is known as Froude's number, right? And is very useful for open channel flow, right? V divided by under root gl. Next one is Euler's number. It is the ratio of inertial force to the pressure force, right? So is the under root inertial force divided by the pressure force. Inertial force formula, you know, pressure force is pressure into area simply. So pressure into area, and above some modifications. So rho q v divided by pressure into area. So rho a v squared divided by pressure into area. Further, you can modify this area cancel out. So and this take this rho inside this py rho. We can write py rho into v square, which can further be written as v divided by under root py rho. P by rho, and this is known as Euler's number. Euler's number. So Euler's number is given by V under root P by rho. Next one is Weber's number. It is the ratio of inertial force to the surface tension force of the flowing fluid. So under root always you will take into consideration. So Weber number is equal to under root Fi by Fg. Uh, Sorry, not Fg. Write this Fs, surface tension force. So surface tension force is called surface tension into length, right? Length of the flow. And above that, already you know the formula for this. No need to repeat it again. So you can directly say rho a v squared divided by under sigma into L, where sigma is surface tension, is the length of the flow. So if you do modification in this, you can get the final form, that is v under root sigma by rho L, and this is known as Weber's number. Right. So almost you are getting some sort of formula for all. Next one and last one is called Mach number. Right. It is the ratio of inertia force to the elastic force of the flowing fluid. So elastic force, when it comes to picture, you will be talking about the bulk modulus, that is K. So Fi upon Fe under root is known as Mach number. So this is K, this bulk modulus of elasticity into the area is called as elastic force. And over that, rho a v square, so area cancel out. So further modification, if you do v under root k by rho, this under root k by rho is known as speed of sound, right? This is known as speed of sound, speed of sound. So local speed of the object to the speed of sound, this ratio is known as Mach number, right? Where c is equal to under root k by rho. So this is regarding the Mach number, right? So Mach number usually defined by the ratio b by c.